Hello guys, back. We're going to go over some more stuff here. I'm going to make several videos going over some individual stuff that came up in the comments to help you guys out. A lot of this really works better for me to make a video of than try to type it in to the comments. Besides that, I think if I make a video, anybody else who has the same questions or anything, it might get to them a little quicker, a little easier. I know some people never read the comments. So the first thing deals with what does it really mean, ohms per volt. You know, when I was talking in the meter loading video, I was talking about different impedances, and then I got talking about your VOM meters. They're usually rated per so many ohms per volt. Now there's various varieties of them. The newer ones, or the newest ones that were out there, or at least newer ones that were produced, were 20,000 ohms per volt. Before them, a lot of them were at 10,000 ohms per volt, and it halved again before them. And then you had the 1 and 2,000 ohms per volt meters that were out there, early 30s. You'd see some of them around the mid 30s. And they started to increase the ohms per volt. But what does that actually mean? The first thing I want to explain, make sure that there's no misconceptions on it. Here's a VOM, which, by the way guys, I bought this at a garage sale. It's in pretty decent condition, as you can see. Handle's real good shape. It's a little Heath kit. Well, not so little, but I got this for $5. Came with the leads. They're pretty nice, in really good shape. Negative, and it is truly a kit because I took it apart and checked the batteries, which were no good, and put some new batteries in it. Anyway, let's talk about this 20,000 ohms per volt. Now that's DC. On AC, the meter actually tells you, and if I can come in here a little closer, hopefully that's not glaring. There. It's 5,000 ohms per volt on the AC scale, but on the DC scale it's 20,000 ohms per volt, and that's typical of your VOMs. Now, when they're talking, say on the DC scale, 20,000 ohms per volt, what they're talking about is the setting that you're set on. This goes from 1.5 volts to 1500 volt scales. So all this is meaning is whatever scale you're on, you take that voltage times the 20,000 ohms. So at 1.5 volts, take times 20,000 is a total of 30,000 ohms impedance. Go up here, it's 5 volts times 20,000, or 100,000 total ohms impedance or resistance to the leads. At the 50 volt scale, it's 50 volts times 20,000, and that'll be 1 meg, and it just continues on up until you get your highest scale. It's not what you're actually reading. Like, let's say you were on the 50 volt scale, because you're going to read something that's definitely above 5 volts, maybe 10 volts, 15, 20, 30, whatever, up to 50 volts. It will always be 1 meg at that point. Now, where this is derived from, and I don't, reading schematics is kind of a pain, but when you're switching this switch through, you're switching in resistors or switching them out depending on which direction you're going. There's a set of resistors that's in there that creates a voltage divider. And where all this comes from is wherever you got this set at, a certain amount of resistance is switched in. It's tied in series with the meter, so that then when you're checking that particular in that scale and voltages in that scale, you don't peg the meter. It reduces the voltage, so it's something that the meter can use, and you can get an accurate, get a reading on it. So consequently, the higher the voltage scale, the greater the resistance has to be to drop the voltage so that the meter can read it and not peg, because this meter only takes a certain amount of voltage to bring it to full scale. So that's where they're deriving the 20,000 ohms per volt, is from those resistors that they've got in there in that voltage divider that's hooked to the switch, so that when you change whatever scale that you need to check your voltages, you switch those in. Now it comes from that. There's a few other resistors plus the meter's resistance. Meters do have resistance. Now, one other thing I want to clarify is I did the meter loading video just to give you some ideas about, meters do require a certain amount of energy from the circuit to operate. And I had already done, I think it was like one of the troubleshooting videos or something, where I talked about voltage tables, like in a lot of Sam's manuals have, Sam's Photofax. And I talked about where, they'll have a lot of times something wrote in there saying that the voltages in there typically were taken with a 20,000 ohm per volt meter at, say, 117 volts line voltage or 115 volts line, where it was plugged in, and so forth. And then they might even had certain other conditions, like if it was a multi-band radio, maybe they did this when it was in shortwave or broadcast mode, and they checked the voltages maybe with the volume either all the way down or all the way up or something like that. Each one has kind of different set of instructions or something where how the radio was set up when they took the voltages. But they always, a lot of them will give you and tell you that it was a certain type of meter that was used. And those that do, you will find most time is a certain voltage per ohm. And I'm pretty sure I mentioned then that if you're using a digital meter or a VTVM, that your readings will probably be higher. Plus, also, I know I mentioned that if you're running without going through a variac, you're running straight off your line voltage, most likely your line voltage, your house, is much higher, probably 5-10 volts or more higher than what was in those instructions. So expect, in both cases, expect a higher voltage than what's listed. Now, why did they use VOMs is more or less because they figured that most of the time, back in the day, repairmen made a lot of house calls. And to take a VTVM out there, with the vast majority of VTVMs are designed to be plugged into the wall, and considering back in the day that there was not a lot of outlets, you're lucky if most rooms had one outlet, let alone any more than that. A living room or something like that, or front room or whatever you want to call it, may have had 2 outlets. So trying to find an outlet available to plug in your VTVM might have not been a real good idea. Then plus you have to let it warm up, really preferably an hour, and everything else, where a VOM does not plug in. It makes use, when you're checking voltage and current, it makes use of the energy. the power from whatever you're measuring. Yes, they do have batteries. The batteries are only for ohm scale. And RCA, and I think I know at least two others, but I couldn't really off the top of my head remember who they were. But I know RCA for sure did make a battery operated VTVM. Again, it'd still have to warm up some to get stable. So in any case, most of your repairmen took a VOM out. So if you're going to give them a schematic with voltages on it, then it's probably a good idea to use the same equipment that at least they're going to start out in the field with. Now granted, they get back to the shop if it's something more than just something like they can throw a tube in or a fuse or something like that, some real simple fix, they're going to bring it back to the shop, and then they're going to use their VTVM most likely. Now, what about, let's look at some calculations of different meters and see how that affects our voltage reading on a load, say a resistor that we're reading a voltage drop across. Now I went back to the same circuit, and I hope you can see that all right. Anyway, it's just a 10 volt supply, 100K resistor, and a 1 meg resistor, and they're both in series. And then I got my meter hooked up. Now I'll measure across the 1 meg and measure that voltage. Mathematically, assuming ideal wires, no drops in the wires and everything, and then that my resistors in here are exactly as they state. In other words, 100K is 100K and the 1 meg is 1 meg. Then this will have 9.1 microamps current flow, and the voltage drop across the 1 meg will be 9.1 volts. Now in the previous video I showed both the calculations for one of these meters, a digital meter generally around 11 megs or 10 megs, and a VTVM around 11 megs. But I went ahead and rewrote them in here, and we end up with 9.9 microamps. That's with the digital meter at 10 megs, and a voltage across that 1 meg of 9.0 volts, just a tenth of a volt off. Now what about this meter? 20,000 ohms per volt. Since we're measuring 10, we'd go to the 50 volt scale. 50 volts times 20,000 ohms gives us 1 meg input resistance, which I got here. 20,000 ohms per volt at 50 volt scale is 1 meg resistance on the wires. That's what the circuit's going to see. That's when I hook it in. Well, that's hooked in parallel to the 1 meg. So basically just basic parallel circuit that ends up with a 500K equivalent resistor. Add it to the 100K, do the division out, and we get 16.7 microamps, and the voltage across this resistor, what this meter would read, be 8.35 volts. Quite somewhat down from the 9.1 ideal voltage that should be there. What if we take an older meter that was around 10,000 ohms per volt? And I don't have exact history on exactly when. Generally you would have been seeing a lot of 10,000 ohm per volt, but sometime during the war and right after, I think by the time you get in the 50s, you're pretty much going all, or at least late 40s and early 50s, they're going all to 20,000 ohms per volt. So I don't have this, carved in stone. I don't know exactly the exact dates or anything. But anyway, prior to these, they had 10,000 ohm per volt. If they were set with a 50 volt scale, which a lot of them were, then you'd have 10,000 ohms per volt at 50 volts. On that scale, it would give you 500K total impedance or total resistance into the meter. Again, doing the parallel, we come out with 334K now equivalent resistance. Add it with 100K, do the math to find the current. Voltage times divided by resistance gives us 23 microamps, rounded off. That would give us a voltage reading of around 7.7 volts on the meter. We continue down lower to 5,000 ohm per volt. At 50 volts, 250K. Do the addition and the division, you get 33.4 microamps, 6.7 volts read. Go back in the 30s, a lot of the meters back then, at least the mid to early 30s, 2,000 and 1,000 ohm per volt meters. 2,000 ohms per volt at 50 volts only gives me 100K on these leads. So we do out the math and everything and come out to 52 microamps at 4.8 volts. Now, the final thing that we end up with the 1,000 ohms per volt at 50 volts is 50K. Do the math again, you know, the parallel and everything. Get a 48K plus 100K. Doing our math again, we get 67.6 microamp draw and a voltage reading of only 3.2 volts. So what I want you to notice is as these meters got lower impedance or lower resistance on these leads, they drew more and more current from the source and from the circuit, and as they did draw that more current, we had greater voltage drops in the circuit across other points, which changed what we were seeing when we were reading the actual voltage drop we wanted to see. Everything started changing. Loading it down kept dropping the voltage lower and lower and lower. So if you got a meter that you found and you want to use, and you have a circuit very similar to this at 100,000 ohms per volt and you're on the 50 volt scale, if it should be 9.1 volts, you're going to read 3.2 volts. So these meters were very inaccurate. But that's the difference between each one. Now, to give you some other ideas about what's going on here, let's take this down here. We're on DC plus. We'll bring, yes, you guys can really see that. There we go. We'll bring the meters in. We're going to hook up, we're going to set this to resistance. We're going to hook up or measure the actual resistance of this meter on the different scales. So we're at 1.5 volt scale on our DC, 20,000 ohms per volt, and as you can see, that reads 30.2 K ohms. So 30K ohmage. I know it's kind of hard to probably see, and this light's wanting to shine. Take that away. But there's a little K there. So anyways, 30K. Now watch it as I go up. We'll go to the 5 volt scale. We go to 101.1K. 50 volt scale. Now we're going to 1.002 megohms. 150 volt scale, 3.012 or 11 megohms. 500 volt scale. At the 500 volt scale, now we're at pretty much the equivalent of what this meter is, 10.13 megs. Now it's the highest scale of 1500. We're 30.3 megs. Now if you was to measure voltages on that scale, that'd be fine. You'd have very reasonably high impedance going into it, very little meter loading. The biggest thing you got to realize is that it's going to be starting to become real difficult to read real low voltages. Now if you're reading, say, 1500 volt scale That's going to be in here. And if you're reading like something 300 or 400 volts, yeah, that's fine. But if you want to know if it's, say it's supposed to be like 435 volts or 430 volts, that's going to be rather difficult to actually pinpoint out exactly. So you'd want to go down a lower scale. But if you wanted to do that, you could. So that's something I wanted to show you that it does. But now let's look at something else. I've got my VTVM running here, and I got it on DC positive. I'm going to show you what it does. Alright, it's on the highest scale right now. It's about 11.1 megs. That's 1500 volts. Go down to 500 volts, 11.1 megs. 150 volts, 11.1 megs. 11.1 megs, that's the 50 volt scale. 15 volt scale, 11.1 megs. 10 volt scale, or 5 volt scale, 11.1 megs. And at the 1.5 volt scale, 11.1 megs. It stays the same. VTVMs stay the same all the way through. VOMs, on the other hand, don't. They change as you go through. And these change a little. It's auto ranging, but I can go through and it'll change from around about 11.3 megs at the upper scale, the highest scales, and when I get down the lowest scale, it's right at 10 megs. So your digital voltmeters will have a slight change across the board, across their scaling. Even if they're auto scaling, they're doing the same thing. But you can pick the ranges if you want by hitting this button. It'll be either range or scale or something on them that you can actually punch through and select your own range and scale. So I hope that the math is not too difficult, but I hope you can see that, you know, meter loading can be a reality thing. And so, you know, when you're running a 10 meg, you get 9 volts, and it should be 9.1, but a very old meter at 1000 ohms per volt, you only get 3.2. And I hope the understanding of what ohms per volt really means, I hope that I got that through as well. Again, it is only, you take that rating, that 20,000 ohms on this meter, and you multiply it times the voltage, or times this number, and that'll be your resistance. So if 1.55, you take times 20,000. 50, you take times 20,000. 150, you take times 20,000. 500, take times 20,000. Or 1500, you take times 20,000. They all work the same. And that will tell you the true resistance or impedance of your meter when you do that. It has nothing to do with what you're actually measuring. It's not 20,000 ohms per volt, you know, times whatever voltage you're reading. It's times the scale that it is. And the higher that number is, the better the meter is, the less loading it is on the circuit, and the more accurate read you get. The lower that is, that number, the more load it pulls, more current it pulls from the circuit, the greater load it is, and consequently a more inaccurate reading. Your voltage readings will go down as this number goes down. So as this number goes up, your voltage readings goes up. So, but if you're generally always using something like this or a VTVM, it's not going to make a whole lot of difference. Everything stays pretty accurately. I mean, the VTVM is the best at staying dead on no matter what scale you're on, but these are close enough and do a pretty decent job. So, kind of lengthy explanation, but I hope that answers some questions and everything. And if you have any more questions, just leave them in the comments and we'll go over it again. So until next time, thanks for watching.